Hello, it's now time for Euler number 8. So it gives us this massive, enormous number, and it tells us that the four adjacent digits that have the greatest products are 9, 9, 8, and 9, and they're there in the number. And it's going to ask us, instead of the four numbers that have the greatest products, what are the 13 numbers that have the greatest products? So how can we do this in Scala? I think the answer is that we can use a special function called sliding, which will go over a sort of collection of things, and you imagine it as a sort of sliding window going over the collection. So it'll return an iterator where the first bit's going to be this 7316, the next one's going to be this 3167, the next one's going to be this 1671, and so on and so forth. And all you do is, once you've got this iterator of all of those things, you just take the products of each set of those four numbers and see which one's the biggest. And you can probably see how that's going to generalise to be correct for 13 digits as well. But we're going to, I always like to do it, like, check in with just the four digits first. As usual, this, definitely isn't the most efficient solution, but it's hopefully one of the simplest ones. I imagine if you want to do this sort of properly, you could possibly use the facts that there are loads of zeros, and anytime you have a zero, that's not even a candidate. And there's probably another thing you can do that's kind of like sliding, except you divide by the last digit from the previous set and multiply by the next digit from the next set or something. But I probably could do it, but I just don't. I don't really see the need to. I think this sliding thing's gonna work. And there's a lot of docs about sliding Euler, so you've got the sort of standard documentation, which is yep, this one just says it takes a sliding window over stuff, which is the one we're going to use. Oh, it's gone. Which is the one that we're going to use. I don't know why that's closed now. Oh well. Well, there it is anyway, and I'll link this in the description. And the other way is some people find this sort of visual ref helpful. I think this one's a bit crazy because it's it has the second parameter where it's you don't do every next element, you do every s. I don't know how to pronounce it, but yeah, every s elements instead. For us, s is just going to be one. But so this is just a generalization, and again, I'll link this in because it's kind of interesting. Alright, so why don't we just give this a go and try and make it work for the case where it's we've got where we try and do what the sort of example was, where we just take four things. So I think the first thing we've got to do is pass everything into numbers, because obviously it's a big old string at the moment. So we only want to take the things that are digits. That's why we have this isDigit function. I think we need this because if we don't have it, we'll end up with loads of new line characters. Then we want to turn stuff into digits. That does exactly what you think. It turns the digit, the sort of character of 6 into the int 6. So yeah, it takes a sort of character or a rich character. Ooh, lovely. To an int, which is good. And then I don't think. So let's think about the bigness of the ints. So the biggest this could possibly be is 13 nines when we come to do the real thing, and that's going to be greater than. That's equal to 9 to the 13, which is greater than 10 to the 12, which is greater than the maximum int. So we need something a bit bigger than ints. So I think probably longs will suffice. Is there a too long? Too long. Yeah, there we go. Yeah, great. Because if we don't do that, we'll end up with horrible integer overflows. And now we actually just go ahead and use the sliding of 4 for this particular case. And then we want to, I guess, map each. So this represents an iterator of 4s. And then all we want to do is just do, I guess, underscore dot products to get us the products of the four things, and then we just want the maximum. We don't actually care about the individual numbers, I guess. We could actually just do actually, why don't we just do dot max by underscore dot products. There we go, and then that'll give us the numbers, and then there's our answer. And then what I'll return at the end is I'll just return like the answer itself, so we can see the actual numbers and also the products of the answer, the products, which is what the question actually asks for. But I just thought it'd be kind of interesting to like see which numbers it actually is. So let's see if this works and see if it gives us the answer of 9989 and 5832. Okay, great. It looks like it's given us the right answer. So, I mean, I'm just going to go ahead and plug in 13 and see what happens. 13. Unlucky for some. Well, apparently that's the answer. Let's see if it's right. Let's see. Yay! All right. Well, I guess that's kind of it. Yeah, I mean, this one wasn't that difficult actually, but I think it's because we've got this sort of silver bullet of sliding. I guess if we didn't have sliding, you'd probably do this in terms of fold left and essentially just implement sliding. I think, and I think an interesting thing is like if we had a sort of I guess, infinite kind of stream of digit. Well, not infinite, but a really large stream of digits. I think the solution would still work really well. If instead of having this as like, if we just have this as like an iterator of digits, doing sliding on it is still gonna like produce an. It's not gonna run out of memory as it's producing that iterator because it'll only need to take like 13 at a time. So it'll only be scanning it 13 at a time. So it doesn't have to hold on to. It only actually has to hold on to remembering the max value. So I think this would actually work with like a really big stream as well. So that's kind of cool. But I don't actually know. That's just speculation. Anyway, thank you for watching, and thank you if you stayed to the end as well. And I will see you next time for number 9.